Well, thank you, everybody. Thanks, Frederick, for setting up this this event and the Zoom and everything. Thanks so much, and welcome everyone. Welcome to also to the audience. That I'm sure it's quite numerous in Australia. It's about 7 or 8 p.m. there. Thanks so much for joining at this time of the day or the evening. Today's speaker is distinguished Professor Kerrie Mengersen. We're particularly pleased to have her here, and thanks so much for accepting this invitation. Distinguished Professor Mengersen, she's been elected member, she is elected member of the Institute of Mathematical Statistics. She has been president of the International Society for Bayesian Analysis. And since 2008, she's an elected fellow of the Royal Statistical Society. Her focus research-wise on using and developing new statistical and computational methods to solve complex problems. She's primarily known for her contribution in the application and the methodology for Bayesian statistics, but also meta-analysis and application in statistics, particularly in medicine and environmental science. She has co-authored 3 books and more than 250 research papers. And from what I read on her webpage, she considered the best things about her job to help people to make use of their data and to help them make the best decisions based on this data. So it's a great pleasure to have Professor Mengersen here, and I would like to give you the podium for this talk. It is entitled "Calling All Citizen Scientists Using Bayesian Statistics to Advance Public Input into Scientific Analysis." It looks extremely interesting.
Thank you, Umberto, and thank you to everybody who's listening. I'm really honoured to be part of this series, and I'd like to acknowledge also the 2 research institutes that I work through at QUT. The first one is an Australian research centre, Research Council, Centre of Excellence in Mathematical and Statistical Frontiers, or ASIMS, and the other is our new Centre for Data Science at QUT. And I want to talk about the topic, as you can see here, and I want to start off by just explaining why I want to talk about this. So probably about 15 years ago, we were looking at the question of where do these rock wallabies live? So these are brush-tailed rock wallabies native to Australia. They live in very remote conditions, and we were looking at habitat modelling for these rock wallabies. We don't have a lot of data, but we have information from experts. So how do we elicit the information from experts and then take it out of their heads, put it into a quantitative form that then we can use for modelling? So the second question then came around monitoring orangutans in Indonesia. And so these orangutans then live in high nests, and the common method of counting how many orangutans there are and where do they live is by observing these nests. It's very difficult to get good observations, but of course there are many locals. And so how do we get the information from locals in a form that we can then use for our quantitative models? And the third example is a few years ago, I found myself in the Amazon in Peru, working with a conservation group to create a corridor for jaguars to move through. And the question here was, where do these jaguars live? How many are they? And can we then identify the characteristics of the forest that would be best for to create this corridor? Now, this involved both locals and experts. And so really this work has been building up to how do we use this information that we have from people to inform our statistical models? So the research team here involves a number of people. I'll refer to the papers as we go along, but I'll just point out the people in our QUT team here, and there are many others. And so I talk on behalf of their work, and I acknowledge their contribution to this endeavour. So I want to talk about some of the case studies in detail, and in doing so then be able to explain what we're doing with these kinds of data. And the first example here is in koala conservation. So we need to know where these koalas are. They're difficult to see in trees. And especially in Australia, we've had terrible bushfires. And so the question is, you know, how many koalas are they and where do they live? And so what we wanted to do here was to combine the citizen science also with drones and virtual reality. And so looking at new tech solutions for being able to monitor koalas. So I'll just show you the area that we worked on in first instance. It's a small area near Brisbane here. And we wanted to know where are the koalas and how many are there? So what we did then was we used drones. So we used drones for thermal imagery. Now, I'm a terrible drone flyer. And I think I'm a better analyst than a drone flyer, but thankfully there's some people who could fly these drones better. And we took thermal imagery of this, and we were able to use then the sort of the classification algorithms and object identification algorithms to be able to determine a koala in a tree from these thermal surveys. So it's pretty exciting in and of itself as a project. The other sort of data that we had then was from crowds. So we had ground source information. So this was people who walked through this area and observed koalas and then recorded them. We also had experts. And so some of the experts were able to identify on the ground then in the area where these koalas might be. But we can't bring all of the experts to the area. So the question was then, how do we access the experts who aren't able to attend in person? But if we look first just at the ground survey data and then the presence data that was obtained from the thermal surveys, you can sort of see where we have presences in the area and then also where we've just mapped some pseudo absences. So this was really our data set based on these two sources of data. As I said, we then included expert information through the use of virtual reality. So we took 360-degree photos and then we immersed experts in these photos and on these images, and we asked them how likely is a koala to inhabit this, this space, and what are the characteristics that make you give your answer. And we asked also about the uncertainty of their answers as well. Now, as you can imagine, that allows us not only to bring experts to the area, but also take the areas to the experts. And so we could obtain information from experts around Australia. So the kind of information that we elicited from experts was around this point estimate plus the uncertainty, and also the range of plausible values for that probability of a koala being at the site. We also then needed to talk about how to elicit. So over the time, coming up with training material and also calibration of the probabilities that people are giving. Then we needed to match the elicited responses to a distribution then that we could use for analysis. So here we matched the elicited responses to a beta distribution. If it was a continuous distribution, we used the normal or t, but for a probability, we used a beta distribution where we had a point estimate and uncertainty, and then translated that to a form then of a distribution that reflected their response. And so the types of beta distributions that we see here, we could then think about representing that expert's information. So we also had some environmental predictors, and now we're in the business of building models. And so the kinds of models that we built for this were a logistic regression based on presence absence from the two sources of data, the ground observations and the thermal imagery. And then we used the expert elicited probabilities of observing a koala to fit this beta regression model based on the beta distributions that we'd constructed. And then we combined the estimated coefficients from these two models using an inverse variance weighted combination. So if we do that, then we can see the results we get from the ground surveys, ground plus experts, ground plus thermal imagery, and then all three types of information. And from this, then we can understand which of these predictor variables are important for being able to identify where these koalas might be. So if we just look at information from experts, information just from the surveys, and then when we combine them. So we get these different probability or the aggregated probability maps for habitat distribution for the koalas. So combining these three sources of information then allowed us to get improved effect estimates and predictions. And we can use then to better estimate and predict presence of koalas. So this then has real benefit for conservation, but also for public policy and for planning. Now, ongoing work in this is to develop methods for eliciting and combining information from experts and locals. We've only just sort of scratched the surface of that, to develop methods to combine the regression estimates from the different models that we might fit with these data. And importantly then, to improve the confidence in the citizen science data. Now, one of the very common questions we get is, how reliable are these data? And can we really use them for modeling, especially when we have access to designed experiments and observations, scientifically obtained observations. And then we also have access now to machine learning, AI, and automated analysis. But crowdsourcing in ecology is really common, and we have a lot of this information. In ecology alone, we have hundreds of citizen science projects. Some of the common projects are eBird, Zooniverse, iNaturalist, and there's a toolkit that's been developed on crowdsourcing in citizen science in the US, for example. You can use Mechanical Turk, for example, to be able to conscript citizens from around the world to be able to work on the scientific project. So there's a lot of energy in this area. And one of the questions then is, how do we use this information and how do we make sure that it's reliable? And that's the area that we're really trying to target now. So I can't describe it in the koala example, but what I'd like to do is to describe how we're trying to address that problem in another project. And this is called Virtual Reef Diver. So if you Google Virtual Reef Diver, you'll find this project. The question here that we were trying to address is that we have the Great Barrier Reef. Now, the Great Barrier Reef is 2,300 kilometers long. It's big. And there are certain points along the reef where there are long-term monitoring studies. And so we have that kind of scientific information. But there's a lot of the reef where there's no such information. So how do we fill in the gaps there? Well, we can use satellite information, we can use drones, we can use different kinds of imagery, and we can use citizens. So what we did then was to build a virtual Great Barrier Reef, and we said there are any number of divers out there with their underwater cameras. What if we geotagged those images to our reef, and then we can use citizens to go into those images and classify them with respect to the amount of coral? Then we can take that information and we can include it in our statistical models, and then we can expand those models and get better estimates of the health of the reef across the whole area. So we take, for each of the geotagged images then, we identify then for that image areas that we then ask the citizens to classify as to whether it's coral, sand, algae, and so on. And with the combining then underwater imagery from either citizens or from drones, and we're also combining citizen science. And this citizen science can be through web-based 2D images and also through 3D imagery and virtual reality. So it's a fun project, and we get a lot of information and a lot of activity on our site. So the question then is, how do we make sure, again, that this information is reliable? Well, we've got our underwater image classification that can be undertaken through statistical machine learning techniques, our sort of automated methods, for example, spatial mixture models, POTS models, dynamic factor models, mixture PCA approaches, regression trees, matrix factorization, neural networks, convolutional neural networks, and so on. So many different approaches that we can use for images through these kinds of methods. We also then have citizen science. So we have these classified images with estimates of coral. So we could use, for example, that information, that crowdsourced information, just as inputs to our statistical machine learning algorithm. So that could become the training data that we might use for a neural network, for example. The other option is that we actually analyze that citizen science information in its own right, as I've talked about. Or we could look at combining the statistical machine learning and the citizen science information. And this is really at the interface of these two technologies, if you like, or these two sources of information, that there's a lot of interest right now. So is it better to use one or the other? Do they serve different purposes, or can we look at combining them? So in this study then, the question again, or the elephant in the room in this case, is how reliable are the data? So what we wanted to do then was to look at how we understand modeling error-prone citizen science information. We could ignore the information, or we could assign a weight to each observation based on the perceived accuracy, or we can actually estimate that accuracy, accounting for the difficulty of the task. So if we do this then, I'll skip this, one of the models that we created for this was a 3+ model. So we took a 3-parameter model, like a model that estimates the user ability, the task difficulty, and the guessing. And it was a logistic model because we have 2 outcomes, coral or not coral in this case. And we also include spatial information because images that are closer together will have the same kind of difficulty. So that's hence the 3+. We found from this model a better model fit compared to just the 3-parameter model, the usual sort of item response model. We also had improved correlations between the estimated and the true difficulties. We improved prediction accuracy, and we had better estimates. So this was a promising approach to obtaining then. The important things here was to estimate a user's ability, taking into account the task difficulty, the images that they were assessing, and whether they were guessing. So we have the model here, as you can see. I've just written it here, but I won't go through it. But what we're doing then is saying we have an estimate of the target class from or an assertion whether it's in the target class or not from a citizen or a user. We modeled that as having some true underlying probability of it being coral or not at that particular site in an image. And then we take into account the ability of the user, the difficulty of the image, and the discrimination parameter, and also the guessing parameter here. One of the things that I said was that we can get this information from crowdsourcing via Mechanical Turk. So we put some of these images into Mechanical Turk, created this project. This is a royal we. It was led by Agus Santos Fernandez and Julie Versaloni in our group. The images were displayed on Amazon Mechanical Turk. This was a new experience for us. We collected data over a period of time last year. Participants were paid for this, and each participant was assigned up to 40 random images and asked to classify 15 points per image. So we got a lot of information from this, this work. In fact, we got so much information from this that we needed then to understand how to handle data sets that were too large to be fit directly into one machine or on an HPC. Now, in our communities then, we understand a little bit about how to handle these kinds of data sets through divide and conquer approaches, divide and recombine approaches, and so on. And there are alternatives. So for us, for example, we just used a different way of creating those subdivisions or those shards. And then this really helped with the analysis. Now, there's obviously a lot of work that's being undertaken in all communities, statistical, machine learning, AI communities, computer science communities, around this understanding how to deal with these kinds of images or these kinds of big data sets. So the kinds of results that we obtained from this then was that in some test cases, we had asked marine scientists to annotate the images. And so we could use those then to say, well, we have some truth from the experts or from the marine scientists. And then we also can compare that with what we estimated through this model. You can see here that there's pretty close fit between what we saw in the test data and what we estimated in terms of their ability. And so we could then classify citizens in terms of their, whether they were a beginner status, a competent, experienced, or expert status. So now we can do all sorts of things with this. We can say, we'll only use the experts or the expert and experienced people. We will provide personalized feedback to the citizens who are beginners, demonstrated beginners, and then we can increase their expertise. And so there's many ways that we can use this information. And importantly, we can incorporate a weighting system in our analysis to account for then the ability of the citizens. We also obtain, as we said, the difficulties of the categories. So we can try to understand how difficult it is to estimate different components in our images. And you might see here that one of the hardest categories to classify was so-called soft coral. We can learn about reef health, so in terms of the predictor variables. So we understand, for example, through this process that heat waves and cyclones have this really negative effect on the proportion of hard corals, and that there's no-take marine reserves and middle reef shelves tend to have substantially higher proportions of corals. And so we obtained this kind of information from these models as well. When we come now to look at whether we should use this citizen science data as opposed to just our long-term monitoring project data, we can see that the results are quite compelling. If we use all of our data, that's the citizen science data and our scientific data, we get much better coverage, much closer fitting models, and it's really worthwhile. So this was encouraging to us. We can see also that we get a lot more granularity in the results when we combine the models. So the top plot here is just when we use the long-term monitoring results, and then the bottom plot is where we use all of the data, including the citizen science data. We similarly see that kind of granularity when we go to looking at the standard deviation. So we get a much better or much richer profile of the uncertainty of the predictions of coral across the reef when we use all of the data. We can also compare the citizen science data to the machine. And so the dot on this plot is the estimate of coral cover based on a neural network, convolutional neural net. So this is the estimate obtained from that and what we see from this plot here is that the machine learning method works well, but some of the citizens actually do better. So we can perhaps obtain then a subset of the citizens who are doing as well as the machine. And so this is work in progress to understand how we combine or how we compare these two types of data. We see in this comparison here, the difference between the convolutional neural net that we fitted and the citizens' consensus probabilities in terms of sensitivity, specificity, accuracy, precision, and a correlation coefficient here. So we find that we obtain similar performance under both approaches, apart from the Matthews correlation coefficient. And again, this is still work in progress. I'm sure there are people in the audience here who might have some ideas, comments, working in this area. I'd love to hear from you. So the summary then is that this citizen science data has strong potential to complement statistical machine learning and AI methods. It's a form of data that is rich, there's a lot of it, and we can learn how to increase the reliability of the data and then the trust in this kind of citizen science data. It also then raises interesting questions for us in the broader issues of Bayesian modeling. And so we can think of the issues in Bayesian modeling that we've touched on here as in priors, in terms of our models, in terms of what information really lies in the citizen science data. What about computation? And lastly, what about provenance? These data are owned by citizens or by organizations. How can we access them in a way that respects the privacy and the ownership of those data? So stepping out a little bit and thinking about what the current conversations are in Bayesian statistics, we can think about those conversations in the literature in terms of priors, models, computation, and the kinds of inferences or decisions that we may want to make from these kinds of data and in fact in all kinds of data. So if we look at then priors, the kinds of conversations that are happening in the Bayesian statistics literature are around whether we need automated or bespoke types of priors. How can we build adaptive priors? So priors that will learn as we and perhaps should learn or may not learn as we proceed with our knowledge. So we understand that we have this sort of sequential updating or Bayesian learning approach where the posterior from time t becomes the prior for time t+1. And so that way we can propagate the information from one time period to another. And there are other ways then of forming adaptive priors. We can also look at uninformative or semi-informative or fully informative priors. So a lot of discussion still about what comprises an uninformative prior. How do we actually construct these fully informative priors and the effect that that might have on our analysis and whether that's reasonable. An interesting question then too is if we use these fully informative priors, then we need to think about goodness of fit approaches as well. Goodness of fit approaches typically are when we take our model outputs and compare them to the data. But in this kind of analysis, the data is only one part of the input. It's the data plus the priors that we're interested in. And so we need to account for that when we're looking at our goodness of fit measures. You can also think about models, the kinds of models that we built, whether they're fully parametric, semi-parametric, or non-parametric. A lot of effort into that, whether we have full likelihoods, empirical likelihoods, or no likelihood at all. Probabilistic models. We want our models to be flexible. We want them to be robust. And the robustness is to the model uncertainty. Always, the model is not complete. And so how do we allow for that uncertainty in the model statement and account for that in the model, in the analysis, and then see that in our outputs? We want models to be transferable. So in the situation that we're typically told not to do, we build a model in one, based on one data set in one setup, and then we transfer it or extrapolate it out of that setup to another case. And so we want to do that, but then we want to create a modeling setup that enables us to do that. We want our models to be regularized so that when we're in high dimensional setups, we can reduce to the core information and induce sparsity in our modeling. We also want to have our models be adaptive to learn as in the same way as we want our priors to learn. In terms of computation then, the current conversations, the literature is around scalability, subsampling, dealing with the large data problems, and also thinking about how we might do pre-computation in many of our algorithms. So instead of having to compute these terms at each stage of the analysis, can we do some pre-computation that then would save us time? Approximate algorithms like approximate Bayesian computation, sequential Monte Carlo, and variational or approximate Bayesian computation and variational Bayes as approximations, and then sequential algorithms like sequential Monte Carlo. So these kinds of approaches in which there's a lot of work done and work in our group as well. And again, we want our computation to be adaptive and, as I said, provenance preserving. And in terms of the inference and the decisions, we can think about design. So we can consider the kinds of modeling that we're doing here about telling us about the data that we need to collect. So we have adaptive designs, but also in a case where, for example, if we have a lot of data, then we could lay down a design over those data and pick up the points that we're interested in order to be able to answer a particular question. So if we have a question of interest and we think about what would be the perfect design for that question, then we can lay that design down over our data, pick out the points, the observations, the design points, and then we can analyze only those data. And this has many advantages in terms of thinking about an experimental design approach to the data collection. So we can have adaptive designs, we can have experimental designs in terms of data collection. We can also, there's many questions around estimation from these models and optimization and the duality in estimation and optimization when we're in a big data setup. Uncertainty quantification certainly plays a role in all of this. Uncertainty quantification through the estimation process, and then also the model choice and the model uncertainty process as well. Questions of multiple testing, questions of model averaging, and also what is the intrinsic information in our data and how do we understand that and then feed that through to our analyses. So there's a large amount of literature in the Bayesian statistics community that overlaps a lot with the statistics disciplines, the machine learning disciplines, the computer science disciplines, and all of this then we can think of as in data science. And can never go past a good quote, but thanks to Nate Silver saying in the past 10 years, it's hard to find anything that doesn't advocate a Bayesian approach. Now, that was a while ago that he said this, but I believe that it still holds now. So I'd like to spend a little while then just touching on some of these current conversations and some of the ways that we've been thinking about addressing these. And you can see the purple points here. I'm just going to touch on 3 points. Semi-informative priors. I want to talk about provenance preservation and also intrinsic information. And again, this is in these topics. I'm sure people in who are listening to this have some experience in this and also some ideas and some comments. I'd be pleased to receive those. The first one then is around priors. So I want to think about how we might use, again, people for the elicitation of priors and the setup of these priors, and in a different form now to how we've talked about it before. So now we're thinking of high-dimensional regression as an example. There's many ways that this could be used. And we have a design matrix, in this case, X. And in this case, we have, the classic situation, small n, larger p. And so we have a large number of predictors and a smaller number of samples. And so we have our model, which might go y equals x times beta, where beta are our regression coefficients, then plus some vector of mean shift parameters. We want this to be sparse to allow for outliers in a small number of observations, and then we have epsilon. So in this case, then we want the betas, the regression coefficients, to push towards 0 in order to be able to just highlight the real signals in the data, which variables are really contributing to this, the estimation or the prediction of our response y. So the priors that we might impose on our parameters here, both on the betas and on this delta, this vector of the mean shift parameters, may be a horseshoe prior, so really spiked at 0. And the question then is, how do we choose these priors? How do we choose the priors for these hyperparameters? And so this is something that's very difficult to ask of an expert or of a person in the field, in the particular field that we're working in. But what we can do then is to think about eliciting information about the future data rather than the parameters. And so the question is, what's a reasonable choice for a prior distribution from a parametric class in this case? And one way that we can think about that is considering the prior predictive distribution and then use a form of history matching. So this history matching idea is used in many different areas, infectious diseases, computer models, petroleum reservoir modeling, galaxy formation modeling, rainfall and climate models, and so on. So the way that this works in this situation, when we want to be able to elicit about priors, is that we choose a set of summary statistics based on the data to be observed. And then for each statistic, we specify a set of values that would be surprising or unsurprising if they were observed in a set of data. So, we can propose a set of candidate values for the hyperparameters, and then we can compute the probability, given those parameters and the model, what's the probability that the the data that we would derive from that model and the summary statistics from those data would be surprising or unsurprising. And then we can accept or reject the candidate values on the basis of that. So what we do in this case is we're building up a set of potential values for our hyperparameters that would allow us to say these values would produce data that would not be surprising, that would be plausible. So in our sparse shrinkage regression estimation problem, we can think about setting up those terms of what's surprising and unsurprising in terms of our log S squared, so in terms of the variance, and then also in terms of our cross-validated R squared. And so if we do that, then we say what values would be surprising or unsurprising, and then we can generate values for the hyperparameters. We can then work out whether that's going to lead through our prior predictive distributions to values that we would see the data would lead to data that would give us summary statistics in terms of the log S squared and the cross-validated R squareds that we would see as plausible or implausible. You can see that the points here that I've circled are just from the third iteration of the modeling here that gives us a zero implausibility estimate. So these might be points we can take. And if we look at those sorts of points here, we can say this is the prior predictive density for the two summary statistics for two zero implausibility hyperparameter values. So from this, then we can start to build up what would be the distribution for these hyperparameter values that would lead to plausible data. So we're using information, elicited information in a different way now to be able to create these semi-informed priors. The second issue that I'd like to touch on is in computation, and in this case in provenance. Now, there's a lot of work in the computer science literature and in this coming into the statistics literature around, well, obviously analysis through a single database, analysis through distributed computing, but and in this case then the provenance or the privacy is through encryption. We still use encryption, but we can also now look at decentralized computing and edge computing. And so this work is filtering through to this, well, it's actually, there's many areas in the statistics community that are very active in this area, but then it's filtering through to all of the statistics community and becoming part of the general toolkit. And so we see this as a really, an area of great intersection between the different domains. Now, the thing is that there's a lot of work that's been done in this field, and this sort of idea of federated learning and federated analysis is really taking off. And so that's fine, but what we don't see very much is how to do this in practice. And so for many of the problems that I've talked about, then we need these kinds of tools, and actually putting them into practice then, and having these examples are really important for our health agencies, our Indigenous research agencies, and so on. And importantly, and also in our virtual reef diver projects and similar conservation projects. So I've just given here a brief outline of some of the work in federated learning. You can see here some commentaries, some approaches through Bayesian networks, through neural networks, through time series data for spatial data. And the dates on these indicate that this is still new work, and there's an emerging area, and there's a lot of interest in this. And of course, then in the ways that we might use surrogate likelihoods, and Michael Jordan and others have been really active in this area. So, so a lot of interest in this, and our motivation in coming to this problem was, and is, the primary motivation is through the Australian Atlas of Cancer that we've built. So we want to be able to combine cancer data sets across states and countries. We have an interactive cancer atlas. It's online. You can search for the Australian Atlas of Cancer. We have about 20 different cancers at small area level. It's underpinned by a Bayesian spatial model. And this required us to bring together data from the different states of Australia. It was a heroic effort in and of itself to bring these data together. And so a federated approach may be one where we don't have to do that. And so we can respect the privacy, the integrity of the data, and so on through this form of analysis. So we have a collaboration with the IKNL, the Cancer Agency in the Netherlands, that's been doing some excellent work in this area. And I just commend this as a way that we see a really useful practical example of using federated analysis. So they have a software advantage, and we'll be using this in the coming year or so in our analysis as well. You can see that they're combining data sets across, combining information without combining the data sets across the different countries. So Netherlands and Thailand, and also Netherlands and Italy and so on. So we leave the data where they are, do the analysis, and bring the aggregates or the summaries back and iterate through the development of the parameter values. So the way that we can work, for example, for a federated GLM is we calculate the MLE for beta at each step by efficiency scoring. We do that for each of the data sets, and then we bring the estimates together to then be able to construct the betas that we require, the coefficients of our model. So in the virtual reef diver setup then, we want to do something different now, where we want to preserve provenance by not combining the images. Now, this also has the advantage of not creating this huge database, but we want a federated approach instead. So what we've been looking at is then federated matrix factorization. So we have an adaptive learning rate, and we use the federated stochastic gradient descent approach to minimize the loss. And so there's a lot of benefits in this. It's applicable for streaming data, which is helpful for us. There's privacy protection and learning efficiency. It reduces the training time on the model, and we maintain a high prediction accuracy when it's applied to multiple data sets. So again, this is work in progress. So the third area that I'd like to touch on, which is also work in progress, is understanding the dimension, the intrinsic dimension of our data. And in this case now, our citizen science data is more by the contribution of wearables, and also by the playing the game that we might video and then analyze. But in this case, what we want to know is what's the intrinsic dimension, what's the complexity of the play as the game moves through. So what we want to do here is think about a small number of dimensions or variables that can effectively describe a high dimensional data problem. So we can use, as I said before, we can use matrix factorization for this, but we can also use the approach I'll talk about in a minute to understand then what this intrinsic dimension might be, and understanding also or allowing for the fact that this intrinsic dimension could vary within the same data set. So there are many cases where this might be something that we would want to allow. So our aim then is to cluster regions with the same local intrinsic dimension in a given data landscape. So if we think about just one, no change in the intrinsic dimension, so the same intrinsic dimension over the whole space, then we can think about our data that's going to have an unknown intrinsic dimension that's constant in the region. And it's going to be defined in terms of the second neighbor of each point. So what we do is we take an observation, we look at the distance to its neighbor, and then that observation, its distance to its second neighbor, and the ratio of those two distances is going to have a Pareto distribution, and that Pareto distribution is going to have a parameter, D, that governs that, and that D is what we can call then the intrinsic dimension. So we're interested then in estimating that parameter D. Now, if we're in this heterogeneous setup where we have local differences in the intrinsic dimension, we can expand that then to a mixture of Pareto distributions. And we can understand then for each observation or each point then it belongs with some probability to a particular manifold, to a particular area with a particular intrinsic dimension. So we can impose priors on our parameters here, and then we can use the Bayesian machinery to be able to estimate D. So in a simulation study, for example, here we have just 5 Gaussians. We have different dimensions across the space. We've simulated some data from these Gaussians, and then we retrieve the dimensions. And it's just an exhibition of the ability of this model to retrieve these different dimensions. So when we go to use this then, in practice, the way that we've been using this is in sport analysis. So this is intrinsic dimension in basketball. This is player tracking for a basketball game. We want to know how the placement of the players in attack and defense related to the success of a play. So what's the difference between the attack and the defense? What's the difference between a home team and an away team, a winning team and a losing team? What can intrinsic dimension tell us about plays and teams? So we took these data then,
Professor,
and we considered a...
Professor,
yes.
No. As you asked me, just letting you know that it's 45 minutes since you started. So just so you know.
Perfect. Thank you. Thank you. So, so we have this intrinsic dimension. We have this particular game, and these results then show us. I've just illustrated the results here, where we can see a difference in the intrinsic dimension between between games that are lost and games that are won. And so, so this is some indication of differences in the complexity of play in these teams. We can also see then the posterior means of the intrinsic dimension over the course of the play for the first 3-point field goal. And so you can see there's low intrinsic dimension, low complexity at the start of that play. It becomes very high complexity during the course of the play, and then reduces towards the end at the time of the goal. So this kind of information then can reveal the kind of complexity, the unexpectedness in the plays in these games. So again, this is work that's to be explored further. So then that's the 3 points that I wanted to mention from the broader suite of Bayesian literature and some of the ways that we've been exploring that. There's a lot more in the Bayesian literature, of course. What we find then is that that's the broader picture in the Bayesian literature. That's been motivated by the citizen science data. And the citizen science data itself has the opportunity to provide scientific insights, but we need to understand then how to analyze those data, how to interpret them, how to integrate those data with our broader suite of data sources. The data might also motivate then new mathematical and statistical challenges and solutions for Bayesians, and also for many others. And on that note, then I'll hand back to you, Umberto, and I thank everybody for their attention.
Thank you very much, Professor Mengersen, and thanks everyone who's here attending. So we have some questions in the chat. Please, if you have some questions you want to pose, it's probably better if you write in the chat, so then I will pick these questions up. So there are a couple of questions that are related to your 3 parameters model that you show sometimes at the beginning.
Yes.
The first one is from Marisa. How do you estimate the citizen's ability in this 3 parameter model?
As part of the analysis, then we can set up priors on those parameters. So on the ability parameters, on the difficulty parameters, on the pseudo guessing, and on this discrimination parameter that just says how quickly we go from 0 probability to a probability of 1. So we set up the priors on those. We have our model, we have our data, and then we can obtain the posterior estimates for theta given the other parameters in the model. So, so it's a common sort of item response model. It's used in many cases. The canonical example is in an examination context where we have students answering exam questions. We want to understand the ability of the students given the exam questions that the difficulty of the questions that they've answered. So we can obtain from that then the ability of the students and also the difficulty of the questions. It's a similar sort of model that we're fitting here.
Mm-hmm. And we have another question on model selection, but first, since we are talking about the 3+ model, someone asked what was representing the notation of YIJK, what type of spatial adjacency metrics did you use on the spatial terms that you denoted with BJ?
Thank you. So the spatial term was in the J, so that's in the images. So what we said, or what we modeled was that images that are closer together have a similar kind of difficulty. And so we wanted to take that into account. And so the term in the model, the B, that was the difficulty of the images, that was modeled through a spatial prior. And the spatial prior was a Markov random field prior, which is just in terms of its neighbors. So it was saying that a point would be similar to its neighbors, and the neighbors here was any contiguous area. So for a particular point, that term then would be have a normal distribution based on the mean of the difficulties in the surrounding areas. And this then builds, if you like, this sort of local smoothing or local spatial correlation structure across the space.
And well, first of all, before going on with questions, honestly, I had to admit my ignorance on the existence of citizen science. I mean, I had to Google it up. And for if others like me are in the same situation, there is a citizenscience.org, and probably there is quite a lot of information. It's quite interesting. I assume that there are lots of opportunities for statisticians and data scientists. So thanks for that. And Sebastian is asking a question on model selection. So can you estimate, are you able to estimate the evidence that, of course, would be useful to compare models or even choose the prior? I'm not sure about the last part, but yeah, can you estimate the evidence? I suppose it's talking about the Bayesian evidence, or the denominator of the Bayes theorem.
Right. Okay. So you can integrate over the various terms. So depending on the type of analysis that you're doing, then you can obtain any of the marginals. You can obtain the overall baseline, if you like, by doing, for example, Markov chain Monte Carlo. So you can sort of get an idea of what's typical, though, is we want the probability of the model given the data. You can also look at like the probability of the data if you want, given the other information as well. And that can come out of the MCMC analysis or any of the approximation methods. You're right in terms of those, and it's easy to wave your hands and say, yes, you get this, but some of the calculations of those terms, it can be quite difficult depending on the kinds of priors that you've imposed. Yeah, there's quite a lot of work done on understanding what the impact of priors are in a Bayesian analysis, and it turns out to be quite interesting. So, for example, some of the work that we've done, this was with Judith Rousseau. It's slightly a little bit to the left. I'm sorry, Umberto, but if, for example, you have a mixture model, and typically what we would do in a mixture setup. So we think of data that has different subgroups, and we don't know how many subgroups it has. And so what we can do then is we can overestimate the number of subgroups, and then we say, well, if some of the subgroups have small weight in our analysis, then we can just get rid of those. Now that works in a setup where that is governed by the priors that we put on the weight term. And in fact, it depends on the hyperparameters of those priors. And those hyperparameters must be defined in terms of the dimension of those different subgroups or those different components. So there's this kind of understanding of what happens with the way that we specify priors And that impacts then on the posterior distribution and on the types of decisions we can make about what is the true number of components in our population, the true number of subgroups. It's quite interesting to be able to understand this. For example, that's in one case with a mixture model, and it looks very different when we look at a hidden Markov model, for example. So just understanding the role that priors play in a Bayesian analysis is still a large part of the Bayesian literature.
Thanks so much. We have another question. I will go to that in a moment, but yeah, I would like to stress the importance that not everyone is aware of doing, for example, prior predictive simulations. We have seen something related to that in the talk, and that's a very powerful tool. Yeah. We have a question from Ove. How can you use counterfactual CS data? I'm not really sure what does maybe I can ask Ove to unmute and pose the question.
All right. So I picked up the abbreviation CS from prior knowledge about that. So it means citizen science data, whether it's science or not, I'm not sure. But a lot of citizens have opinions in sports and in games in general. What would happen if that and that had not happened? So there is a kind of pool of available counterfactual beliefs among citizens when it comes to games. So that prompted me to question, in relation to your current conversation overview in Bayesian statistics, if there is any conversation around the counterfactual analysis, perhaps in relation to game theory in Bayesian statistics.
Yes, thank you. There's quite a lot of conversation around the use of counterfactuals, and especially in causation. And I think that parallels the kind of conversations that happen in the other communities. And that's a really rich area. It's interesting you mentioned that in sport, though, because I haven't actually thought about how we might best capitalize on that. So perhaps that's something that we can consider.
Okay, thank you.
Okay, so I think that we don't have other questions. Please do write in the chat if you think about something more. Would you give us? Can you give us some maybe hints or some suggestion for how to get involved with this type of citizen science? What is the Well, now I figure out that there's some website that I can look at that. Is there some other way that you are aware of?
Yes, thanks, Umberto. There are various, well, there are many, so there's a couple of ways. So there's a lot of groups that are practicing citizen science. As I said, there's in ecology, but also in medicine and so these groups, there's, for example, an Australian Citizen Science Association that's sort of gathering up these kinds of projects in the different areas. And then there's, so it would be the same in other countries. And there's also then websites that are promoting this kind of crowdsourcing information. So there's different kinds of citizen information, as was pointed out, you know, whether we call this science or not. What we aspire to is that someday this will be called science, but and because these data are around, so you know, my preference would be for a well-designed study, and you know, that we can then we can understand the data and the reliability of the data. But this kind of information that we are obtaining from people offers a great opportunity. And so I think it behoves us to try to provide some degree of understanding about it and some tools for being able to improve the reliability of this and to use it in an appropriate way. So there are platforms that promote the citizen science. For example, we use Mechanical Turk, so you can look at those sites. There's also open data sources for citizen science data. in terms of the analysis, then if anybody wants to get in touch with me, then I'd be very happy to you know, put them in touch with people that we're working with, and then also talk about projects here as well.
Thank you very much. Just one curiosity. I was very interested with your with the figure that was showing that, for example, some citizens were doing better than a machine learning algorithm. What I'm not sure I understood was whether they were better in some specific tasks rather than uniformly better.
Yes, sure. So this was in a specific task. So we were here talking about the ability to estimate the coral cover, the proportion of coral in an image. Now you can imagine that there's a lot of complexity in the images. There's images that are taken up with different machines or different cameras, different depths, and so on. And so training a neural network, in this case, training a neural network requires quite a lot of information and to be able to cover those different kinds of conditions. And in some cases then, when we have this either a smaller amount of information or we have these quite different conditions, then people may be able to do a better job. And so we saw some of the people in this who were able to, you know, be able to identify, you know, coral cover in a broader range of conditions than the network. Again, this is work in progress. And also, when we had this situation where we found this, then we went back, and the people we were working with went back and said, well, we've got to just we can tune our neural network better. And of course, that's the question. You know, you can make it better, but of course, then there's the balance of the transferability or the generalizability of those kinds of models. So, as I said, this interface between the artificial intelligence, machine learning approaches, and the citizen science data, I think, is a really interesting area for us to be looking at, and something that we need to do so that we can really start to use these data in a trustworthy manner.
Is there maybe one publication that you would like to point out to highlight some of the approaches that you've considered today? Of course, there were many topics covered.
Yes.
Sometimes at the end of the talks, there is this long list, reference list that nobody looked at, and this time there was none, which is unusual.
Sure. I'd like to point out the work of my colleague Edgar Santos Fernandez. So he's the first author on a number of the papers that we've been publishing with using citizen science data, and then he refers to other literature as well. So that Edgar Santos, S-A-N-T-O-S, and then Fernandez, F-E-R-N-A-N-D-E-Z.
Thank you very much. Well, I would like to wrap it up now. It's 9:05, I suppose, in Brisbane. And thanks everyone for joining in. Please, if you're interested in further talks, AI talks, you can look at aitalks.se, and you can subscribe to a mail list to be alerted. Well, that's it from us. Thanks so much, Professor Mengersen. It was a pleasure, really.
Thank you very much, Umberto, and thank you very much, everybody, for listening.
See you in the real world.
I hope so. All right.
As soon as possible. Bye-bye.